The course that I teach, have taught for the last year, I suppose, has been practical English. So practical meaning useful. Useful for certain types of conversations. So, in the context of business, in the context of entertainment, culture, music, in the context of science and technology, you have keywords, high frequency keywords. And this is what I try to highlight for you guys and show you how they're used, right? I mean, learners of a foreign language have hundreds of thousands of words to learn. But you don't need to learn every single word that's in the dictionary, every single word that's ever been invented. You only need to learn the specific range of words that are practical in the area that you're interested in. So, if you're studying for an exam, you want to be taking an academic English course. If you're studying for, negotiating with foreign clients, then you want to be taking a business English course. If you're studying for travel, then you want to take a travel and tourism English course, or pick up a book that'll teach you these kinds of vocabulary. That will be practical for you. So recently we've been looking at different kinds of academic subjects, from biology, infectious diseases, health and nutrition, fitness, to culture and entertainment and travel. We're back to science, and we're going to be looking at modern inventions, the things that we use on the day-to-day basis, the technologies that we depend upon in our daily lives, and how they came to be. Who were the inventors? How do they work? Now, I can't explain too much about any one invention. We're going to look at 10 different inventions. So really it's just a general introduction. Of course, we'll have time to look at more of these inventions in further detail in future lessons. So there they are. I've given them in the worksheet. What are the following inventions? How are they used, and how do they work? We have the clock. What's a clock? What's a clock? The clock is a device that helps us to know the time. You probably look at the clock maybe 100 times in a day. Everyone wears a watch. Everyone has their mobile phone, their computer. The clock is always running. Why are there 12 hours and 60 minutes in an hour? How did we come up with this concept of time? Compass. What's a compass? Well, if you drive a car, the direction that you're driving in is very important. So a compass is what helps us to know which direction we're moving in. Nowadays, most people use the GPS, but that has a built-in compass. So we'll look at what a compass is and the science behind how a compass works. Telescope. A printing press. A steam engine. An engine. An electric generator. Where does our electricity come from? The power that we use, the power that we get to use our computers and our phones and our lights and our heaters, our refrigerators, right? Energy. Where does electricity come from, or how do we get electricity from these energy sources? If you've been taking lessons at Webby, you're very familiar with, or whatever we call it nowadays, you're very familiar with these kinds of conversations already. We talk a lot about time, don't we? We talk quite a bit about directions and the compass. We talk a lot about where energy comes from. Welcome. We have 13 people tonight. That's great. The light, the electric light, the telephone, and the computer. So it's just a quick little introduction to each of these things. Honorable mentions, things that I could talk about but won't have time to, are the radio, the camera, the car, the airplane. But we can come back to these in another lesson. Now, up at the top, we have these words here. The first word is, let me close that, a compass, okay? Translate the word. Open up your Yodao dictionary and, find the translation, write it down. A computer. Digital. So we talk about technology as being either mechanical or analog or digital. What's the difference between an analog clock and a digital one? The analog clock is mechanical. There are some gears and springs that move the hands of a clock around the clock face. It's a mechanical clock. A digital clock shows you numbers on a screen. So when you think of digital, think of numbers and computers. Digital music, like when you listen to a musician play on an instrument, the sound is being produced by the instrument. When you're listening to music on an MP3 player through a speaker, you're listening to a digital representation or a digital copy. The sound has been recorded and encoded into some digital format and then played back. Most technologies nowadays are digital. An engine. An engine. An engine is the component inside a car or an airplane where the fuel is burned to produce the force, the movement that can then turn the wheels or the parts of the machine. So any kind of factory, any kind of vehicle, any kind of machine in a factory or vehicle is powered by an engine, an airplane. Okay. Basically, it's where fuel is burned to produce the force to propel the machinery to move, to do work. Fuel is the stuff that is burned, whether it be wood or oil or food, if we're talking about how we get energy. A generator. A generator is kind of a machine that takes the force of movement and converts it into electrical energy. We will get a chance to look at that. Industry. Industry is sort of production, manufacturing done by machines. You should know what that is by now. Invention. So the invention of the wheel, the invention of fire were the two greatest inventions that brought us out of, our primitive nomadic existence into the civilized world, where we could use tools such as weapons and shovels and hammers and fire to forge new tools. So innovation, invention, industry is all about tool making to make our lives easier. A lens, camera lens, piece of glass. A magnet. We'll look at a video that explains a magnet. I don't want to spend too much time on that. Mechanical. So I mentioned the difference between something that is digital and something that is mechanical. A digital clock versus a mechanical clock. The mechanical clock has moving parts, whereas something that's digital is not moving, but it's a computer circuit running, running an electrical current through a series of transistors. A microphone. It's the kind of device that can convert sound into an electrical signal that can be transmitted or amplified. Navigation, having to do with using a compass. A needle. A compass has a needle. It's what points in the direction north. Orbit. The sun and the moon and the planets are in orbit. A pendulum. Not terribly important, but before we had the electric clock, we had the mechanical spring-powered clock, and there were various ways to keep the gears in motion. A pendulum is something that swings. You could swing a pendulum, and it would just, like through the force of inertia, keep swinging until it would stop, and you have to start the pendulum again. And that's what kept the clock moving. Physics. So physics is a branch of science having to do with the forces in the world, like gravity and electromagnetism, heat, light, all this cool stuff. A sundial, a shadow. You'll get to know that in a minute. A telescope, a transistor, a turbine, and a weapon. So a telescope, you'll get to know what that is soon enough. A transistor, again, you'll get to know what that is soon enough. A turbine, part of the electric generator, and a weapon. Okay, so there's your worksheet. I've kind of gone through all of the terminology. Pay attention to these keywords. Hopefully most of you are in the intermediate and above. If you're not, don't stress about it. Just, keep showing up, listen carefully, read, and take notes. That's all I expect. And try to enjoy. In this lesson, we will be looking at 10 of the greatest inventions that influenced the history of the modern era. In other words, the modern era is the industrial technological era, when we started burning fuel to power engines. That's the modern era, around the 18th, 19th, 20th centuries, the modern era. Now we're in the information era. We're still in the modern era, but anyway. We're sort of in the digital computer information era now. Anyway, we'll be looking at these 10 inventions, how they are used, prominent inventors and scientists, and how these technologies have evolved since the time that they were invented. So the first one is the clock. What are the components of the clock? The clock, well, okay. What is a clock used for? In the first picture, we have an hourglass. And so this is not a clock, but it is a time measuring device. It helps us to measure the duration of time. So, there's sand that passes through a piece of glass, and the duration of time it takes to have the sand go from one end to the other is about an hour. That's why they call it an hourglass. The old-fashioned equivalent of the stopwatch, or the timer, let's say. Here we see the sort of the traditional mechanical clock, and that swinging little disc below the clock is the pendulum. Here we see the inner workings of the mechanical clock, all of these different gears, and a digital watch. So a clock is a device that is used to measure and keep and indicate time. We can measure the duration of time. We can indicate what time it is when we look at a clock. The time on the clock is measured in hours and minutes and seconds. And the larger units of time are measured in days or the lunar month and years. How did that come to be? So this is the sundial. And if you look at the shape of it, it's circular. It's got this, I don't know what you call that. Let's just call it a, I don't know what that's called, I'm sorry. But we have the stick, the pointer, let's call it a pointer. Okay, we have the pointer in the middle. The sun casts the shadow on the pointer, and the shadow, as the sun moves across the sky, moves the shadow. The pointer casts the shadow, and as the sun moves, the shadow moves. And the shadow moves over the different markings. You can kind of see the Roman numerals around the circle. So this is how we can tell time with the sundial. So the sundials were the first devices that man used to keep track of time. And its use dates back as long as 6,000 years. So from what we can gather, the Egyptian civilization was the first, the first known civilization in recorded history, going back roughly 6,000 years. 3000 BC is when the Egyptian civilization came into being. And they were very interested in astronomy and studying the stars, studying the movement of the sun, because they were a farming society. The same thing is true in China. China invented its own timekeeping system, and I'm sure that societies in all parts of the world were using the sun and the stars as a way of measuring time. But we have, in Western history, we have the Egyptian solar timekeeping system, observing the movement of the sun and the calendar, and it was used for farming. So the sundial shows the time by placing a shadow on a marked surface. The first mechanical clock is said to have been made by Yixing in China in 725 AD. So the first mechanical clock, not a water clock or a sundial. But in all societies, they were very interested in timekeeping, and they used different, mechanical means of keeping time. Not all of them were very successful or very well understood. So we would say that the modern, the modern mechanical clock, spring-driven mechanical clock, from which all other clocks, mechanical clocks, have evolved from, appeared in the 15th century Renaissance period. And that's very important to mention because it was when the mechanical clock became invented, and people could take the invention and replicate it and reproduce it, that we started seeing clocks showing up in town squares and people's homes and so on. And this really changed how how people lived and organized their day and the working. We were able to become more scientific thinking in how we went about our day, rather than relying upon nature and sort of observing the seasons. We used mechanical clocks and started following calendars and organizing our work around these artificial systems rather than the natural one. And the Renaissance is the precursor to the Enlightenment in the modern era, basically. So moving away from the superstitious religious type of a society and the farming society into the scientific one. Today, clocks come in two versions: the analog mechanical clock, which is often circular. The position of the hour and minute hands indicate the time, and digital clocks, where the time is represented in their basic numerical format. There are 24 hours in a day. Why? We'll talk about why when we get to the telescope. This is the compass. So, mapping our planet. Compasses are often used in conjunction with maps, which are oriented to have the north positioned at the top of the map. To use a compass, you place it on the map, and you wait for the needle to get its bearing to point north. And after some adjustment, the navigator can then follow the desired direction. You put the map on the table, and you put the compass on the map, and you make sure the compass is pointing to the top of the map, and then you know if you want to go east or west to turn left or right. How does a compass work? I wish I could tell you. Fortunately, I have a video that can.
Electromagnetism, or the electromagnetic force, is one of the four fundamental forces of nature. It generates light and energy and holds atoms, matter, and the world as we know it together. Electromagnetism is a branch of physics that studies the interactions between electric and magnetic fields. All matter has an electric charge, which can be positive, negative, or zero. Opposite charges attract, while like charges repel. These electric forces bring and hold atoms together. And when atoms gain a positive or negative charge through the transfer of electrons, a measurable electric field will form. If those electrically charged particles start to move, the field will become a flowing electric current and form a magnetic field around it. Under the right circumstances, interacting electric and magnetic fields can continuously produce and sustain one another. This generates an electromagnetic field that transmits waves of electromagnetic energy or radiation into space. The intensity of this radiation is determined by its frequency. These frequencies make up what's known as the electromagnetic spectrum. Near the middle of the spectrum is visible light, such as light emitted by stars, fireflies, and computer screens. On either side are invisible electromagnetic waves. On one end are long, low-frequency radio waves that broadcast television and radio signals, microwaves that carry telephone signals and cook food, and infrared waves emitted by fires. On the other are short, high-frequency wavelengths, ultraviolet, X, and gamma radiation. Unlike low-frequency waves, these waves can pass through the human body, making them useful for medical applications. While electromagnetism has daily applications, it's also the engine that drives the planet as a whole. Thousands of miles below the Earth's surface, a layer of liquid metals churn and flow. This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful radiation in space, leaving us to enjoy a world held together by the strange and fundamental force of electromagnetism.
So electromagnetism, it is the, I don't know, I'm probably messing this up, but you have, at the very smallest level, you have atoms, and atoms are made up of charged particles called electrons, and when atoms collide, creates a kind of a static electricity or friction, which generates electric charge. And because there is so much friction, and movement caused below the Earth's surface by the molten metal, or it produces this electromagnetic field, and that creates a magnetic pull that is strongest at the poles. So, the magnetized compass works having a needle suspended on a pin. It's just a slightly so you can give any like all materials, be it wood or plastic or metal or glass, have electric conductivity. Our own flesh has electric conductivity. Some materials are more conductive than others. Metal is very conductive. So if you rub metal together, you are building up an electric charge in the metal. And so we take a magnetized needle, a piece of metal, a needle that has been magnetically charged just by rubbing it and giving it some friction, some static energy, and it just increases the charge of that metal. And when it is suspended on a pin, it is moved in whichever direction has the strongest magnetic pull, and so it pulls to the south. Yeah. The Chinese. The Chinese invented the first compass, understanding that you could magnetically charge a piece of metal called a lodestone, and they placed it on a very flat, polished plate, and the lodestone would kind of move. They didn't use it for navigation, they used it for divination. I couldn't tell you about that. But the Chinese helped in the creation of the compass, the clock, many other things. You guys should be very proud of your scientific achievements, honestly. Okay, the magnetized needle came into use in the late 13th century when, and after the invention of the compass, we began to have like naval exploration, countries building ships and going off to sail off in search of new lands. Next up is the telescope. So the telescope is an instrument that uses a curved glass lens and mirrors arranged in a way to magnify distant objects to appear nearer. Like most of us wear glasses. You take a piece of glass and you curve it, and it magnifies. That's a telescope. The astronomer Galileo. The telescope wasn't invented by Galileo, but he built a telescope. And his model of the telescope is the one that has been sort of modeled after. Anyway, so Galileo, oftentimes considered to be the grandfather of the scientific method. You don't have to be a scientist to understand the scientific method. One of his greatest achievements. So Galileo is the grandfather of the scientific method, and is one of the greatest astronomers, physicists, and mathematicians of all time. Astronomy is studying outer space, the stars. Physics is studying forces, movement, and mathematics. Okay, so Galileo built the first telescope, and he used that, in addition to his understanding of astronomy and mathematics and physics, to chart the night sky. He really studied the motion of the planets and the phases of their orbits. And again, this is connected to time. Our understanding of the lunar cycles, how long it takes for the moon to, move in a complete phase around the night sky. And through his observations, he came to the conclusion that the Earth is just one of many planetary bodies moving in a system that centers around the sun. So this is the telescope. We're just talking about the telescope here and how important it is. We use the telescope for navigation just as much as we use the compass. In the modern day, telescopes come in many varieties, including the X-ray, radio, infrared, and ultraviolet telescopes. And this is a photograph of the Hubble Telescope. It is the world's most powerful telescope, and it is positioned in orbit above the Earth's atmosphere. So it's floating up in the sky, and it's not hindered by the reflection of the Earth's atmosphere, so it can see much farther without the noise, so to speak, of the atmospheric particles that obscure the telescope. We can't see very well through the atmosphere. It's like looking through a glass darkly. But Hubble Telescope floating up in the Earth's orbit, very, very large, powerful telescope armed with all of these instruments, X-ray, infrared, and ultraviolet, to look tens of thousands, I don't know how far, way, way out into distant space. It was launched sometime in the 1980s, I think, and it gave us these kinds of images. We had never seen anything like this prior to the launch of the Hubble Telescope, and it feeds our fantasies of distant galaxies and alien civilizations and Star Trek and Marvel Universe, this kind of a thing. So, yeah, we're looking at stars, we're looking at galaxies, we're looking at the mystery of space. Okay, next one. Gunpowder. Gunpowder is a chemical explosive. If we look at the photo here, we can see the rifle and the components of the rifle. We have the trigger, the thing that you pull. That pulls the hammer. The hammer goes back. It's pulled back. There's some resistance because the hammer is connected to a spring, which is a piece of metal that is curved, right? So as the hammer goes back, the tension on the spring is increased until the trigger moves past the point, and the tension is released, and the hammer swings back, and it hits where the gunpowder is. Like it hits the chamber where the gunpowder is, and that creates a kind of a spark, and that ignites the gunpowder. It explodes, and that explosion is contained within the barrel, which propels the bullet through the barrel at great speed. So you can kind of see the bullets there, or these little muskets, I think they're called. And then we can see this kind of a stone here. I believe that's called flint. And flint is, how we discovered fire. Flint is a kind of a stone. When struck, it can produce a spark. And, that spark can then be directed towards some incendiary, flammable material, such as gunpowder, to create an explosion. So the chemical contents are sulfur, charcoal, and potassium nitrate. Again, invented by the Chinese. Gunpowder has been used as a propellant. In other words, something that can move something. In firearms, weapons, rockets, fireworks, and the blasting and quarry mining. So explosives. Gunpowder was first discovered in China during the Tang Dynasty in the 9th century. It became widely used for military purposes, making bombs, and could fire projectiles such as arrows or little bullets, metallic bullets. The degree to which the discovery of gunpowder influenced history cannot be overstated. This is what gave, nations, people power, imperial power over each other. And this was a real driver for technology. Defense. How do we defend ourselves from invading enemies? Is what is the motivation behind the many, many technologies that we take for granted, from the internet to the steam engine, on and on and on, right? So gunpowder was like the catalyst. It was the spark for, launching us into the modern era. Gunpowder is no longer used in modern weaponry or industry today, so we just have other more explosive chemicals that we use. But we still call it gunpowder. Next one is the printing press. So here we see kind of a machine, a hand-powered mechanical machine, and the printing press. On one table you have some stamps or some like engraved letters, and those would be placed on a plate, and then you turn a crank and you dip the stamps into some ink, and you stamp the inked stamps onto a page, and you have a book. So the printing press is a prominent part of the foundation on which modern civilization was built upon. Invented by Johannes Gutenberg in Germany in 1450, prior to the invention of the printing press, information had to be laboriously copied, page by page, either by handwriting or by using engraved stamps. So it's just, what we call automation, mechanical automation. The printing press served a great role in the Industrial Revolution, accelerating the rate in which information could be reproduced and distributed. So it was very costly to produce books because they would be, made, one person could make one book at a time, kind of a thing. Whereas the printing press allowed mass production of books, and this made it more affordable, and this, again, fed into the education system. Everyone finally learned how to read and think for themselves. The lowered costs of books, making knowledge more affordable and readily available, again, shifted society towards being more knowledge-driven rather than labor-powered, I suppose. The steam engine. Steam engine is an engine fueled by an external furnace, burning coal or oil to heat water to produce steam. So as you can see in this diagram, we have the furnace where the fuel is burned. The furnace you don't see in this photo, actually. The furnace is off to the right. But the furnace, produces the heat, which heats the water, which produces the steam. And if you've ever boiled a kettle before, you know that the steam makes the kettle, like the top goes pop, 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 pop. So that's a propellant. And if you kind of contain that, you can you can use the force. The combustion force of steam pressure pushes a piston back and forth inside a cylinder. So the steam pushes the piston, and then the piston is connected to a wheel, which moves the piston around, moving it back and forth, connected by a rod and a flywheel into rotational force, which can then move other wheels and levers and machines and so on. So the steam-powered locomotive used the pulling power of the steam engine. After the steam locomotive was invented in 1802, railway transportation became wildly commercially successful, enabling factory manufacturing and urban development, bringing the agrarian farming society into the modern industrial capitalist era. So you were able to carry, large quantities of building material, lumber and coal and iron across long distances. You were able to bring the workers to the mine and the materials back from the mine into the city, where they could then be processed in the factory and shipped out to other cities for sale. Now here's the electric generator. A generator is a device that converts motive power, the movement, the force of movement, into mechanical energy, into electrical power. Okay, and we can use any kind of fuel source, whether it be fuel like fossil fuel, gasoline, kinetic energy such as the power of moving water or wind. It turns in a circle. It rotates around, well, you have a magnet, which we've established what a magnet is, around a copper wire. And again, so you're creating a kind of a kinetic static energy, and that is built up in the wire, and that can be, again, put into a battery or something like that. So here is the inventor of the electromagnetic generator. I think we'll talk about electricity in a future lesson, but we kind of already know what electricity is from the first video, and I want to show you this video as well. So this is how the generator works. And the generator, the first generator is the same principles pretty much apply in all generators, all turbines, all electrical turbine generators. So here we go.
Newton, Lavoisier, Darwin. What do they all have in common? All these science geniuses came from wealthy families. But Faraday, a working-class child, not only joined that highly select private club, but also unraveled one of science's all-time greatest mysteries. Born in a humble family, Michael Faraday experienced the hardships of the 19th century English society. Working at a bookshop, he taught himself science through the books he read. He also managed to go to Humphrey Davy's lectures about chemistry and electricity and was dazzled by them. He wrote a book that summarized the lectures. Davy was amazed and took Faraday on as a lab assistant who assisted him on his trips, where he met other scientists. That's how he learnt about magnetism and the ongoing discussion about its relationship with electricity. Scientists imagined them as different fluids moving through the air and wires with no relation between them, until Ørsted discovered that current passing through a wire moved a nearby compass. Electricity and magnetism were then connected somehow. By this time, Davy had suffered an accident, and then Faraday could do his own experiments. Trying to explain Ørsted's results, Faraday thought that, the same as vibrations of sound fly through the air, making objects vibrate, then maybe electricity wasn't a fluid, but a sort of vibration carried through the air as magnetism. So he designed an experiment. He took an iron ring, isolated it, and wound two coils on the extremes. Connecting one to a battery, he saw that switching it produced an electrical current on the other. Faraday deduced that the coil emitted magnetic vibrations that travelled through the ring, inducing electricity on the second wire. But if changing the magnetic vibrations caused the second current, why not use a magnet directly? He moved a magnet through the second coil and it generated electric current. Faraday discovered magnetic induction, and in 1831, using it, constructed the first dynamo ever, a way to convert movement into electricity. This popularized electricity, democratizing its use and making it possible to be available everywhere.
Let's look at some other sources of energy here. So any kinetic energy, whether it be the power of moving water, wind, or steam, can be converted into electricity through the electromagnetic generator. Solar power is something else. So the modern world relies upon electricity to power its multitude of devices. Burning fossil fuels to heat steam as a propellant to power electric turbines is still the most commonly used energy source. However, due to its limited supply, we need to look to clean and renewable sources such as hydroelectric, wind, solar, and nuclear energy. The light bulb. The incandescent light bulb consists of a glass globe containing a tungsten filament. It's just a kind of a mineral that has properties of glowing when given an electric current. So the metal wire, the wire coated in the tungsten filament is connected to a socket, which is connected to an electrical current. And when the current runs through it, the filament glows, providing artificial light. Thomas Edison did not invent the light bulb. Many people were experimenting with this, but he did develop the commercially successful version of the light bulb, a kind of a light bulb that could be affordably made and mass-produced. Nowadays, we don't just use the incandescent light bulb. In fact, we rarely use it at all because it is not very energy efficient. Rather, we use other sources using different technologies, but we have the fluorescent, the halogen, the LED. As you can see, we could talk all day about how light, how light communicates, like how we use light for communication in traffic, for example. So since the invention of the incandescent light bulbs, inventors have found many other forms of lighting technologies that can provide lighting for different purposes. A spotlight is a very bright light that can be used to shine a directed light over a longer distance than a typical light bulb. Nowadays, most of us light our homes with LED. It's a low-energy, cost-efficient alternative. We were moving quickly because I want to get to the last video. This is the telephone. A telephone allows people to communicate over long distances. It's a combination of a microphone, a device that converts sound into an electric signal. I couldn't tell you how that works today. But the sound is then transmitted over a cable and sent to the receiving telephone that can reproduce the sound through a speaker. So the parts of the telephone are the microphone, and then the transmitter, and the receiver, or the speaker. First invented by, or patented by, Alexander Graham Bell. So, telephones used to be connected by cables, and cities looked like this. And we've moved to wireless, radio communication, I suppose. And we use these towers for wireless communication. In like fashion to the printing press and the steam engine, the invention of the telephone allowed economic growth and technological innovation to develop rapidly due to the power of communication and the spread of information. Okay? Words and ideas matter in ways that we'll never really understand. Wireless communication has replaced the old systems of cables. The mobile telephone supports many more uses than it originally did, but the person-to-person communication through the telephone is still one of the greatest inventions of our species. Okay, computer, personal computer. Personal computers are computing devices intended for personal and commercial use. They feature the microprocessor, or the microchip CPU, a monitor, and the peripheral device. In other words, the keyboard and the mouse. And they run an operating system, which in turn can run applications. Popular modern operating systems include the Mac OS, Microsoft Windows, the Linux, and Ubuntu, and the little green man. This is the inventor of the computer, the mechanical computer, Charles Babbage. Okay. And this is the first supercomputer used by the military in the 1940s. And this is the modern transistor microchip and integrated circuit. Computer transistors and integrated circuits allow electricity to be carried along electrical pathways. Small rapid pulses of electrical signals can be interpreted by computers as binary signals, which make up a kind of language that humans can use to make computers perform a wide variety of tasks. And if that's all gibberish to you, don't worry. I'll have the notes available later, and I have a video which can illustrate it for you. And this is the last one.
Modern computers are revolutionizing our lives, performing tasks unimaginable only decades ago. This was made possible by a long series of innovations. But there's one foundational invention that almost everything else relies upon: the transistor. So what is that? And how does such a device enable all the amazing things computers can do? Well, at their core, all computers are just what the name implies: machines that perform mathematical operations. The earliest computers were manual counting devices like the abacus, while later ones used mechanical parts. What made them computers was having a way to represent numbers and a system for manipulating them. Electronic computers work the same way, but instead of physical arrangements, the numbers are represented by electric voltages. Most such computers use a type of math called Boolean logic that has only two possible values, the logical conditions true and false, denoted by binary digits 1 and 0. They are represented by high and low voltages. Equations are implemented via logic gate circuits that produce an output of 1 or 0 based on whether the inputs satisfy a certain logical statement. These circuits perform 3 fundamental logical operations: conjunction, disjunction, and negation. The way conjunction works is an AND gate provides a high voltage output only if it receives 2 high voltage inputs, and the other gates work by similar principles. Circuits can be combined to perform complex operations like addition and subtraction, and computer programs consist of instructions for electronically performing these operations. This kind of system needs a reliable and accurate method for controlling electric current. Early electronic computers like the ENIAC used a device called the vacuum tube. Its early form, the diode, consisted of 2 electrodes in an evacuated glass container. Applying a voltage to the cathode makes it heat up and release electrons. If the anode is at a slightly higher positive potential, the electrons are attracted to it, completing the circuit. This unidirectional current flow could be controlled by varying the voltage to the cathode, which makes it release more or less electrons. The next stage was the triode, which uses a 3rd electrode called the grid. This is a wire screen between the cathode and anode through which electrons could pass. Varying its voltage makes it either repel or attract the electrons emitted by the cathode, thus enabling fast current switching. The ability to amplify signals also made the triode crucial for radio and long-distance communication. But despite these advancements, vacuum tubes were unreliable and bulky. With 18,000 triodes, ENIAC was nearly the size of a tennis court and weighed 30 tons. Tubes failed every other day, and in 1 hour, it consumed the amount of electricity used by 15 homes in a day. The solution was the transistor. Instead of electrodes, it uses a semiconductor like silicon, treated with different elements to create an electron-emitting N-type and an electron-absorbing P-type. These are arranged in 3 alternating layers with a terminal at each: the emitter, the base, and the collector. In this typical NPN transistor, due to certain phenomena at the PN interface, a special region called a PN junction forms between the emitter and base. It only conducts electricity when a voltage exceeding a certain threshold is applied. Otherwise, it remains switched off. In this way, small variations in the input voltage can be used to quickly switch between high and low output currents. The advantage of the transistor lies in its efficiency and compactness. Because they don't require heating, they're more durable and use less power. ENIAC's functionality can now be surpassed by a single fingernail-sized microchip containing billions of transistors. At trillions of calculations per second, today's computers may seem like they're performing miracles. But underneath it all, each individual operation is still as simple as the flick of a switch.
Okay, so if you missed most of that, to quickly summarize it, computers work, or a circuit board with transistors and central microprocessor work to send small, rapid pulses of electrical signals, which can be interpreted by computers as a binary language. And we can then communicate to the computer to do various tasks. Now, computers, kind of scary, aren't they? Computers have been used since the 1940s by universities and governments. They use those old cathode tubes for, allowing the electricity to pass through, the voltage to pass through, replaced by the transistor. When the transistor was invented, the size of computers and the heat emitted and the electrical voltage required was dramatically reduced, and therefore the personal computer. In the 1970s, they were largely unpopular due to the lack of software. So then we had, people like Bill Gates and people like Steve Jobs. Jobs introduced the idea of designing software that simplified tasks for the average computer user, people like you and me, without having to have the advanced knowledge and understanding of the working of the computer. Computers do the thinking for us. Quotes by famous inventors. Imagination is more important than knowledge. Invention is the most important product of man's creative brain. The ultimate purpose is the complete mastery of mind over the material world, harnessing of human nature to human needs. Necessity, oftener than facility, has been the mother of invention. Necessity is the mother of invention. An inventor is a man who asks why of the universe and lets nothing stand between the answer and his mind. Teachers always asking you, why? An inventor looks upon the world and is not contented with the things as they are. He wants to improve whatever he sees. He wants to benefit the world. He is haunted by an idea. The spirit of invention possesses him, seeking materialization. Wow. What a genius. A designer. Designer is an emerging synthesis of artist, inventor, mechanic, objective economist, and evolutionary strategist. And the only way to do great work is to love what you do. If you haven't found it yet, keep looking. As with all matters of the heart, you'll know when you find it.